Greetings class. So this is now the last topic on unit operations review, and this topic will be on membrane processing. So what are these membrane separation processes? So these are processes in which separation is due to differences in solubilities and diffusion rates through the membrane. So in the illustration that you can see here, you have this membrane and you have the feed here, which is being processed through this membrane. The material that passes through the membrane is referred to as the permeate, and the rest of the material that did not pass through is referred to as the retentate. So it will be discussed in the next slide, the difference between the two. But nonetheless, the purpose of this membrane is more or less comparable to that of segregation. You want only to segregate the particular component that you want to separate from this particular feed having the other components. But the segregation or the separation is not actually 100% efficient, because you can see that there are still orange balls here together with the blue balls. But nonetheless, we have separated a portion of the blue balls from the original feed. Now, the blue balls is the solvent and the solute particle is the red balls or the peach balls. So, unlike the other separation processes, we don't have here the contacting or the intimate contacting of the phases. But we have accomplished separation by the use of a selective membrane. A membrane that selectively only allows a particular component of your feed to pass through. Now, your feed consisting of a mixture of two or more components in the case of membrane separation is passed through, take note, this semi-permeable membrane or barrier. The species may pass through at different rates in this particular semi-permeable membrane, since our separation can be in terms of solubilities and in terms of diffusion rates. Now, in membrane separation, the two products are usually miscible. The products here referred to are your solute and your solvent, or since they both come from the feed, they are said to be miscible, and your feed in the first place is a miscible feed. We don't handle a miscible feed in the case of membrane separation. Now, the separating agent here is semi-permeable as mentioned above, and there is no sharp separation achieved. It's often very difficult to get a 100% separation in the case of membrane separation and in the case of the other separation processes. So I've mentioned about the term retentate and permeate. So the one that passed through or was allowed to pass through the membrane is the permeate, and the one that was retained is the retentate. Now, what is the driving force in the case of membrane separation processes? So it's pressure in the case of gas and vapor feed, and concentration in the case of liquid. Now, difference in partial pressure and concentration across the membrane are usually created by the imposition of a pressure differential or a pressure difference across the membrane. That is in the case of liquid feed. Now, the driving force for liquid separation, this one is in the case of a gas feed. We're using difference in pressure and concentration. But in the case of liquid separation, there is this what we call use of a electric field. An electric field in the case of solute which has ions or charges present on it. So if there are ions present in the solution, the barrier may have an opposite charge than one of the solute in your solution that may get attracted to it, and the rest get to pass through. In that case, we are able to separate our ionic solution. So that is in the case of the use of an electric field. But in some cases, there is this use of a solvent on the permeate side. The purpose of the use of the solvent in the permeate side is to create a concentration gradient. So once there's a concentration gradient, then there would be ease and transfer from one side of the membrane to another. So take note here in liquid separation, A solvent can be added on the permeate side, or an electric field be induced if the solute is ionic, or if your original feed has charges present on it. Now, as to the membrane, so this is a simple illustration of the membrane. The permeate passes through. The retentate did not pass through, but simply was retained on the other side, or flowed on the other side. The phases are, shall I say, separated, or the components are separated based on the difference in their particles, molecules, sizes, or substances when exposed to action of a driving force. So that the separation can be based on this particular species in your feed, particles and molecules and other substances, but they can still be processed through your membrane through the existence of the driving force. So whether we speak of particles, molecules, or substances, they still need the presence of a driving force, so that there will be passage of some through the membrane, and there will be retention of some also on the other side of your membrane. Now, our membranes can be classified based on their use, or their application or objective, and based on their physical characteristics. So the one you see here in the illustration, these are membranes classified based on their physical characteristics or similarities. So the isotropic membrane and the anisotropic membrane. So once those that were classified based on application, and the ones that I have here are just examples. They are not really the only classifications that are used. So membranes can be classified based on the particulate or dissolved solid removal that they can achieve. So one membrane may be efficient over another, so you can classify them based on their ability to separate in terms of particle size or dissolved solids. Now, in the case of water purification, the basis for classification can be based on their hardness reduction. How much hardness, or what is the degree of decrease in the hardness or reduction in the hardness of water based on the use of such a membrane. So that's how we can classify them also. And we can also classify them based on how they remove a specific component of a gas or specific component of a liquid mixture. So this is now has something to do with selective property of your membrane to allow a specific type of your mixture to pass through or not. Now, although they may have different functions or objective, their function is still the same, or their application rather, though they have different applications, their function is still the same. The function is still to separate the movement of species. So the controlling factor here will be the rate and the size of the species that passes through. Now, separation can involve two gases, two liquids, or a gas and a liquid. Now, what are usually these membranes, or how do you physically, how do you tell one or distinguish one from another? So some are thin, some are non-porous, some are polymeric in nature. So polymeric films are also used as membranes or barriers. They can be also porous polymers. They can even be ceramics or metal material, or they can even be liquid, gel, or gas, the membrane itself. So as such, there's no specific limitation as to physically how we can classify this membrane, as long as they accomplish their specific application. However, there is this major requirement for all membranes. All membranes must neither dissolve, disintegrate, or break during the process of separating. They should not dissolve, they should not break, or they should not disintegrate. There was a mention in the previous slide in liquid separation using in membrane separation, wherein there's the use of the solvent on the permeate side. that particular solvent actually used is optional. It could be actually a liquid or a gas depending on the component that you want to separate or depending on the feed that we want to process. But this particular optional liquid or gas used to facilitate removal of the permeate added on the permeate side is what we call as the sweep. They are referred to as the sweep. Now, one major requirement of membrane separation, just like we have a requirement for distillation that relative volatility should be greater than 1, in the case of membrane separation, permeance ratio should be high. And what is this high permeance ratio or high permeance? The degree in which a particular membrane will allow a particular species to pass through it is its permeance. A high permeance ratio ensures that you have a big amount of permeate that passes through and a little amount of retentate on the other side. With one value being large and the other value being small, the ratio of the two will then be high. If the permeance ratio of your specific membrane is small, then it would be difficult to separate your component from the mixture it is mixed with if we use membrane separation. So just like also in relative volatility, to ensure that it would be easy to separate components during distillation, we want that the relative volatility be greater than 1 because that would make separation easy. It's the same thing with membrane separation. So our deciding factor here for the use of a particular membrane is high permeance ratio, which boils down to, let's say, still looking into the difference in solubilities and difference in diffusion rates of your species across the membrane. So speaking of membranes again, if we want to classify them crudely, they can be microporous, so meaning they have small pores but large in comparison to the size of the small molecules. And they can also be non-porous dense membrane, and non-porous. So how does separation happen in such a membrane which is non-porous and dense? So separation occurs by components in a gas or liquid feed, take note, diffusing to the surface of the membrane, dissolving into the membrane material. So the component of the gas and the liquid gets dissolved in the membrane material and then diffusing through the solid and desorbing at the downstream interface. The desorbing portion here is comparable to stripping. The same meaning is attached to it. The transfer from a liquid phase of one component to another liquid phase, meaning you strip that particular liquid phase of a particular component. That is desorbing it, but it already happens on the downstream interface. What does this mean, downstream interface? It already happens at the last part of the process, meaning the final separation, that is, to ensure that you will ultimately separate that component, that solute, from the original feed through the process of desorption or stripping. So in this case, you are using a stripping agent or a solvent that will take out the solute from the liquid phase it is with in the downstream interface. Now, it is easier to recall membranes, as I've said a while ago, based on their application. So let's look into this 5 simple classification of membranes based on their application. So on top of the list is the microporous membrane. Now these membranes behave almost like a fiber filter and separates by sieving mechanism determined by pore diameter and particle size. Take note, the pores in the membrane may vary from 1 nanometer to 20 microns. And your membrane here is as thin as 1 micrometer. That's in the case of a microporous membrane, more or like a glorified filter paper, if I may say. So it has small pores as small as 1 nanometer to 20 microns in size. So very small to control the passage of small particles. The The second type of membrane is the asymmetric membrane. So this comprises of a very thin 0.1 to 1 micron skin layer on a highly porous 100 to 200 microns thick structure. So unlike the previous membrane, this one is inside a 100 to 200 microns thick substructure. So it's within this substructure, this 0.1 to 1 micron skin layer. Its separation characteristics are determined by the nature of the membrane material or pore size and the mass transport rate. So now it has something to do with the rate of diffusion, and it is determined mainly by the thickness of the skin that is being used here, and that skin is your asymmetric membrane. So actually, if I'm going to look at it, since it's already an asymmetric membrane, it's already a complex thing or a composite thing, wherein you have this thin skin layer in a highly porous 100 to 200 microns substructure. That is your asymmetric membrane as a whole. But the signifying, or rather the main thing that separates the component, the solute, or that separates the permeate from the rest of the components in the feed, which is supposed to be retained, the retentate, is this thin skin layer. Now, the next is the electrically charged membrane. So the electrically charged membrane are those membranes which are actually consisting of highly swollen gels, and this has ions. So ion exchange membranes consisting of highly swollen gels carrying fixed positive or negative charges. So gels, swollen gels carrying positive or negative charges. These are mainly used in electrodialysis. This, shall we say, swollen gels which have ions on it. So your key here to remembering this type of membrane is the presence of the word ions. So swollen gels with positive or negative charges, which are called ions. And then we have the last membrane, which is the homogeneous membrane. So it's a dense film through which a mixture of molecules is transported by means of pressure. So this could be the gradient, the concentration difference, or an electrical potential difference. So the separation is through the driving force, pressure difference, concentration difference, and electrical potential difference. And this film can be as thin as 600 nanometers. Those are your 5 types of membrane based on their specific application. Let's go now to common membrane separation processes, the actual processes. So the ones I've discussed are just the intro to the actual common membrane processes utilized in the industry. So we have on top of the list the most common is reverse osmosis. So this is a process by which a solvent passes through a porous membrane in the direction opposite to that for natural osmosis when subjected to a hydrostatic pressure greater than the osmotic pressure. Now, pressure gradient of 10 to 50 bars and can be up to 100 bars are utilized here to ensure that there would be transfer of your component from one side of the barrier to another, or your membrane that is the barrier. To illustrate, so you have here the application of pressure, and you have your component here, and this is your components here of your mixture, and this is your semi-permeable membrane. So through the application of this applied pressure, the direction of flow now of water is from the highly concentrated region to the low concentrated region. Without the application of pressure, the tendency would be from this particular low concentration region to the high concentration region. But since you have an even greater pressure applied on this side, then water from here will be transported, or shall I say transferred to the other side. So that's reverse osmosis. Now, in terms of the determining or quantifying osmotic pressure, it's comparable to the ideal gas law equation we've used and very familiar with in Chem 1 before. So you use the ideal gas equation, PV equal to nRT, and the pi here is the P. We change the P to pi, which is the osmotic pressure. And it's equal to nRT over the volume of your feed or gaseous mixture. Now, reverse osmosis application includes the desalination of brackish water, the treatment of wastewater, the treatment even of surface and groundwater, the concentration of some foodstuffs, the removal of alcohol from beer, clarification of fruit juice, and removal of bacteria from foodstuff. This is just one of the many applications of reverse osmosis. Now we go to pervaporation. From the term vaporation, so there's a process of vaporization, a processing method for the separation of mixtures of liquids by partial vaporization. You partially vaporize a portion of your liquid through a non-porous or porous membranes. In this case, either of the two classification of membranes can be used. So it could be non-porous or porous. So separation through partial vaporization, and as a term pervaporation. Now temperature, however, here in the process is restricted to below 100 degrees Celsius, because if it's higher, water vaporizes at 100 degrees Celsius already. Okay, so you have here the feed, which is liquid. So those that did not pass through the membrane are referred to as the retentate. Those that pass through the membrane are vaporized, and your liquid feed now was partly vaporized, and your permeate now is in the form of vapor. Feed is liquid, but the permeate is vapor in the case of pervaporation. Application includes dehydration of ethanol water isotope, removal of water from organic solvents, and removal of organics from water. So vice versa of the last two. Now, electrodialysis. What about this? So this is used to transport salt ions from one solution through ion exchange membranes. So the membrane has the presence of ions. Now, through ion exchange membranes to another solution under the influence of an applied electric potential difference. So there is this is the key. There is an applied electrical potential difference in the case of electrodialysis. The goal is to transport salt ions from one solution through another, passing through an ion exchange membrane. So this is a sample. Your ion exchange membrane has an electric potential applied to it. So you see these positive and negative loads representing an electric potential application. This is your feed, and then your concentrate leaves here. The diluate is removed on a different side. That's how the concentrate is perceived to be those that have already the presence of the ions, whereas the diluate have those that have lesser ions concentration. So your membrane here is said to be an ion exchange membrane. Now, application is the production of table salt from seawater, though this would be a very expensive way of separating table salt from seawater. Concentration of brines from reverse osmosis, treatment of wastewater from electroplating, wastewater that is a product of electroplating, demineralization of cheese whey, and production of ultra-pure water for semiconductor industry. So I think this one is its appropriate application. Next is dialysis or liquid permeation. I think everybody knows dialysis in terms of its application. Now, dialysis or the process of dialysis is the separation of particles in a liquid on the basis of difference in their ability to pass through a membrane. So this time, our separation here is based on the ability of the particles to pass to a particular membrane. So the membrane is the one that is being selective and allowing particles to pass through it. Now, small solute in one liquid phase diffuse readily because of the concentration differences through a porous membrane to the second liquid or even vapor phase. Passage of large molecules through the membrane is more difficult. So the membrane that is being used here is selective of the pore of the sizes of the particles. So its main objective is to separate by virtue of difference in size of particles. Now this one is an illustration of a dialysis. The separation of very large from very small molecules is based on an attempt to equilibrate concentration. So you could see here that the solution before is blue. And then you have one very concentrated solution inside this dialysis bag. So what happens is, since this is very concentrated and this one is less concentrated, the concentrated portion gets to transfer, or there is a transfer of concentration from the less concentrated region, from the more concentrated region rather, to the less concentrated region. The purpose is, as mentioned here, to equilibrate concentration. As much as possible, we want this region, the blue region, and the yellow region to have the same concentration. So at the start of dialysis, we have something like this. This is how we clean human blood, and at the end we have this. We have equilibrated already the concentration of the concentrated solution here on the yellow bag inside. So that's dialysis. Now in dialysis, we have two terms: the dialysate, the feed solution, the one that is being processed is dialysate, and the diffusate is the solvent. The solvent is the diffusate and the feed is the dialysate. So that's new terms for you. Now dialysis application includes separation of nickel sulfate from sulfuric acid in the case of mining, metal mining, and hemodialysis, the removal of waste metabolites and excess body water, and restoration of electrolyte balance in the blood. So take note, the restoration of electrolyte balance in the blood, because blood before is very concentrated, so we want to neutralize it, or rather restore it to its acceptable level. I'm referring to the concentration of the blood. Now what about microfiltration? So it's a low pressure difference is like say 0.5 to 4 bar cross flow membrane process for separating colloidal and suspended particles. I'd like you to zero in on this, the application: separating colloidal and suspended particles in the range of 0.05 and 10 microns. This is pressure driven through the membrane, which separates micron-sized particles from fluids which are larger than those in ultrafiltration. So the separated particles here are smaller than those using ultrafiltration. Used in separation also of homogeneous mixtures. Now in microfiltration, you have this. So the smaller particles, through the application of pressure in this side, gets to transfer on this side, passing through this membrane. So that's microfiltration. Techniques used in microfiltration may include dead-end filtration, what you have here. So the small particles get to settle on this side and removed. And this one is cross-flow filtration. The feed is introduced to the barrier in cross-flow manner. This is the flow of the feed and this is your barrier. However, your small particles gets to pass through the membrane still. This is cross-flow, this is dead-end flow. Now, application of filtration includes separation of bacteria, paint pigment, yeast cells from solutions, sterilization of liquids, gases, and parenteral drugs. Then classification and biological stabilization of beverages, bacterial cell harvest and purification of antibiotics, and recovery of mammalian cells from cell culture broth. Now ultrafiltration. So the particles that are being separated here is a little bit bigger than those in microfiltration. Pressure is still used to obtain a separation of molecules by the use of a semi-permeable polymeric membrane. The membrane discriminates on the basis of molecular size, shape, or chemical structure and separates relatively high molecular weight solutes such as proteins, polymers, and colloidal materials such as minerals. This is pressure driven and it is similar to reverse osmosis using asymmetric membranes but that are not significantly more porous. And take note, ultrafiltration uses asymmetric membranes, the membranes which has a thin layer within a porous, highly porous matrix. So this is ultrafiltration. So after ultrafiltration, you have already ultrafiltered water. So screening, you have sand filtration, microfiltration, and ultrafiltration. Ultrafiltration application, so pre-concentration of milk before making cheese, clarification of fruit juice, purification of recombinant proteins and DNA, antigens and antibiotics from clarified cell broth, and color removal from craft black liquor in paper making. If you're going to compare and if you're processing water, you have raw water here. This is the retentate side. It undergoes microfiltration. Then the next is ultrafiltration, and then nanofiltration. Then we have reverse osmosis. The final product is the drinkable water. And look at the particles that are being retained, that remains as retentate in this particular separation processes. Okay, so there's even a much better separation than ultrafiltration, and that's your nanofiltration. Gas permeation, so uses a dense polymer membrane which is non-porous such as rubber or polyamide. The solid gas dissolves first in the membrane and then diffuses in the solid to the other gas phase. The feed is at a high pressure and usually contains some low molecular mass species. Now, typically less than 50 kg per kilogram mole to be separated from higher molecular mass species. Now, the pressure gradient needed for gas permeation to proceed is 20 to 40 bar. Now, this is gas permeation. Okay, so you have the zeolite membrane, you have the feed gas in here, and this is your rich permeate gas phase which separated the blue component B from component A. So component A is your retentate gas phase and component B is your permeate gas phase. This is your zeolite membrane. Gas permeation application includes separation of carbon dioxide and water from methane, separation of uranium isotopes, adjustment of hydrogen and carbon monoxide ratio in synthesis gas, separation of air in nitrogen and oxygen enriched streams, recovery of helium from natural gas using fluorocarbon polymer, and recovery of methane from biogas.